Hello everyone and welcome to our video solutions to Superquiz 1. This is from the fall 2021 semester at Cal State Fullerton. The course is Math 302, which is modern algebra. And in this Superquiz, we are going to be assessed on properties of sets, relations, functions, equivalence relations, and it'll have some computations as well as some proofs. In this very first problem, we are given some true or false statements, and this is all about set theory. And in the very first one, we're actually asked about the cardinality of a set. Okay, so I can see, it's a true false about, okay, is the cardinality of the set 6? So a quick refresher, the cardinality of a set, which we denote with the absolute value bars. All right, so this is the cardinality of A. This is asking for the number of elements in A, right? Why do we use these absolute value bars? Because it's how far away the set is from being empty, right? From having no elements. All right, now we look over, we know it's a set because it tells us it's a set. We got set braces over here, and we just want to know how many elements are in here. And it's a true or false, so we look quickly to see if it's right. Are there 6 elements? And we start counting. And we say, oh, look, 1, 2, 3, 4, 5, 6. Hey, that sounds like 6 elements. On the other hand, I do see this Z, right, which means the set of integers, not to mention the Q and the R. Those are infinite sets, so maybe this thing is supposed to be infinity. Let's think carefully, though. Okay, let's go through it one by one. So first, we have the number 3. Okay, I'll just copy that down. Now I go to the next one. And, oh, look at this. We have absolute value bars around, that's the notation for the empty set with no elements in it. So this is asking how many elements are in the empty set. Well, that's 0. Cool. So this is really just a slick way of writing the number 0. Fine. 5 times 4. Oh, come on. What are we doing here? This is 20. Okay, now we get to the interesting bit. So I notice that there's actually some more set braces here. And not to mention there's some absolute value bars around it. So this is actually asking us for the cardinality of the set containing the set of integers, the set of rational numbers, and the set of real numbers. And what we have to remember here is that when you have a set that itself contains sets as elements, it can't see inside. So for example, this set contains the set of integers, but it can't see into the set of integers to see the numbers 1 and 2 and -4 and -8. So when you go to compute the cardinality, it doesn't know about any of the elements in the integers, the rationals, or the reals. All it knows is about what sets it contains as elements. So this is going to have cardinality 3 because it contains 3 sets as elements. And here we should be cautious because we've just noticed we started with the number 3 and now we have another copy of the number 3 in our set. And our definition of a set was that it needed to be an unordered collection of, and here's the kicker, distinct elements. So if you see repetitions, it doesn't count those twice, right? It only has one copy of 3 in there. If you see multiple, you just throw it out. So we actually don't need both copies of 3 in here. And for the cardinality purposes, we don't count both, only one of them. Okay, let's see. Then we see a 7. Hey, no problem there. Finally, looks like we have another one of these interesting cardinalities of a set. So let's see. We have the cardinality of a set. Okay, so there's the beginning and the end. And what's inside that set? Well, we have the empty set, and we have the set containing the empty set. And these are 2 different things. This is an empty set. It has no elements inside of it. This is the set containing the empty set. It has 1 element in it. What? The empty set doesn't have any elements. But remember, when you have a set containing a set, the outside set can't see inside. All it knows is what are its elements, and its elements, whether they're sets or not, that's what it counts up. So this set contains one element, namely the empty set. So in total, this yellow bordered set has the empty set as one element and a set which has stuff inside, but we don't even care what's inside. All right, it has another set as an element. And so in total, it has 2 elements. And so the cardinality is 1, 2, 3. We skip this one, 4, 5. So the cardinality is actually 5, not 6. Okay, so this one is false. Let's go on to part B. The empty set is a subset of every set. Well, I guess this requires us to go to the definition. So if you have 2 sets A and B, A is a subset if every element of A is an element of B. So if I want to prove that the empty set is a subset of every set, then I'm going to have to show that every element of the empty set is in every set. Okay, so let's just take some arbitrary set. Let S be a set. We want to show that the empty set is a subset of S. Well, when does this hold? This holds if every element of the empty set is an element of S. But the empty set has no elements. There's nothing to check. This condition requires us to find an element of phi, or the empty set, and then show it's an element of S. And there are no elements of the empty set to find, which means there's nothing to prove. Right? This is a statement which is vacuously true. Right? So as the empty set has no elements, it's definitely true. Every element of the empty set is an element of S. Right? It's certainly not a false statement. If it was false, you could find some element of the empty set that wasn't an S. But there is no such element because empty set has no elements. All right, so B is true. All right, now we go to C. In C, we're given 2 sets, and we know their cardinalities. Right? The cardinality of A is 28. The cardinality of B is 16. We also know the cardinality of their union. So remember that the union, so A union B, is all elements in A or in B. So if we were drawing this as a Venn diagram, say there's A and there's B, then the union would be everything. Right? This shaded would be the union. Okay, and the question is not about A, B, or the union, but rather A intersect B. So their claim is that the cardinality of A intersect B equals 6. Man, the test writer just must love this number 6. Okay, well, what can we do? Well, A has 28 elements. Okay, so we know that. So all the stuff that fills up A, that makes up 28 of the elements. And then when you union with B, you have 34. When we union with B, there's maybe things in the intersection, and those don't give you anything new. The only thing that gives you anything new is the stuff that's in B, but which is not in A. And how much more did it give you? It just gave you 30. It gave you from 28 to 34, it gave you 6 elements. So there must be 6 elements that are in B, but are not in the intersection with A. Okay, but we also know that the cardinality of B is 16. So if there's 6 elements outside of the intersection, and there's 16 elements total, then there must be 10 elements in the intersection. 10 plus 6 is 16. Okay, so we have found the the intersection cardinality, it's 10. And what did this say? The cardinality of A intersect B equals 6. Oh, no, that's false. That's not true. Right? How might you have gotten 6? Well, okay, it's a distractor, right? You say, look, from 28 to 34 is 6. That's where the 6 is. Right? But this isn't what's in the intersection. This is precisely the 6 elements that were not in the intersection, but were in B. Okay, well, we made it through our first video. I hope this is helpful. Let me know if you have any questions.